Hi. Today we're going to compute the formula for zeta of n, where n is even and n greater than or equal to 2. And this will be the Riemann zeta function. And we're going to use complex analysis. There are many ways to come up with this formula, but today we're going to use residue theory and complex analysis. So in that regard, let's consider the function f of z equal to 1 over z to the n times sine of pi z. And I drew a diagram of the path we're going to use. This is a square. And we're going to call the whole path gamma, and it's going to be broken down into 4 separate paths: gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. And for instance, we might start down here at the lower right corner. The coordinates of that point would be n plus 1/2, comma, minus I n plus 1/2. And this is gamma 1. We're going to go up through the x-axis at n plus 1/2. Notice we want to avoid the integers on the x-axis, so we're going to go between n and n plus 1. The reason for that is at the integers, the denominator here would be 0, and we want to avoid that at all costs. Okay, we continue on gamma 1 to the upper right corner. And the coordinates of that point would be n plus 1/2 and I n plus 1/2. Then we're going to take a left turn on gamma 2 all the way to the upper left corner. At which point we're going to hand off to gamma 3, going down now through the x-axis to the lower left corner, and then we're going to hitch a ride on gamma 4, going back to our starting point. Now this function f of z has first order poles at z equals plus minus 1, plus minus 2, dot dot dot, plus minus n. All these here. All the positive poles less than or equal to n, not including 0 at this point, and all the negative poles as well. Now, the pole at 0 has order n plus 1, n of them coming from the z to the n, and 1 of them coming from psi, or sine of pi z. Okay, let's first look at the integral of f over gamma 1. Gamma 1, of course, was the path on the right-hand side going up. And, of course, z, in this case, will be n plus 1/2 plus iy. The real part stays constant here, where y goes from minus n plus 1/2 to n plus 1/2. Well, let's look at some of the integrand first. The absolute value of sine of pi z on this path equals the absolute value of sine of pi times n plus 1/2 cosine h of y pi plus I cosine of pi n plus 1/2 times sine h of pi y. And since the cosine of pi n plus 1/2 would be 0, and the sine of pi n plus 1/2, the absolute value of that would be 1, all we have left is the cosine h of pi y, which is always a positive thing, and that's always greater than or equal to 1. So in other words, so far we found out that the absolute value of sine of pi z is greater than or equal to 1. Now the absolute value of z on this path is going to be greater than or equal to n plus 1/2. Well, we can see that z is just the distance from the origin. The absolute value of z is the distance from the origin. And the smallest that can be is the 0 to n plus 1/2. Every other place on gamma 1 will have a greater absolute value of z. So in other words, the absolute value of z is going to be greater than or equal to n plus 1/2, which is greater than or equal to n, obviously. Now this implies the absolute value of z to the n is greater than or equal to capital N to the n. Therefore, we can say the absolute value of the integral over gamma 1 of f dz, which equals the absolute value of the integral over gamma 1 of dz over z to the n sine of pi z. Bringing the absolute values inside, this is less than or equal to the integral over gamma 1 of the absolute value of dz over the absolute value of z to the n times the absolute value of sine of pi z. Plugging in our results here, this will be less than or equal to the integral over gamma 1 of the absolute value of dz over n to the n times 1. Well, this simply equals 2n plus 1 over n to the n. Now, 1 is less than n, so this thing is less than 3n over n to the n, which equals 3 over n to the n minus 1. Okay, that's our first result. Similarly, on gamma 3, which is the left-hand path going down, you'll find that the absolute value of the integral over gamma 3 is also going to be less than 3 over n to the n minus 1. Okay, very good. Well, now let's look at the path gamma 2, which is the upper path going to the left. And z on this path is equal to x plus I n plus 1/2. The x varies, or the real part will vary, and the imaginary part stays constant. And n plus 1/2 is greater than or equal to x is greater than or equal to minus n plus 1/2, x traveling to the left. So let's find out what sine of pi z is using our addition formula for the sine of something. Plugging in this for z. Well, this will equal sine of pi x cosine h of pi times n plus 1/2 plus I cosine of pi x times sine h of pi times n plus 1/2. Well, this implies the absolute value of sine of pi z squared, actually, maybe I should say the modulus of sine of pi z squared, equals, figuring the modulus of this thing, this will be sine squared of pi x times cosine h squared of pi times n plus 1/2 plus cosine squared of pi x times sine h squared of pi times n plus 1/2. Well, for n big enough, the cosine h of pi n plus 1/2 is going to be bigger than 1, and also the sine h of pi n plus 1/2 will be bigger than 1. So we can say this thing is greater than or equal to sine squared of pi x plus cosine squared of pi x, which, of course, equals 1. So therefore, we can say the modulus of sine of pi z squared is bigger than or equal to 1. So also then, the modulus of sine of pi z is greater than or equal to 1. And again, as earlier, the absolute value of z to the n is greater than or equal to n to the n, as we learned on gamma 1. Same thing. Therefore, we can say the absolute value of the integral over gamma 2 of f dz equals the absolute value of the integral over gamma 2 of dz over z to the n sine of pi z, as before. Bringing the absolute values inside, this is less than or equal to the integral over gamma 2 of absolute dz over absolute z to the n times absolute sine of pi z. Plugging in our results here, these two results, this is less than or equal to the integral over gamma 2 of absolute dz over n to the n times 1. This again equals 2n plus 1 over n to the n, which again is less than 3n over n to the n for n large enough, which equals 3 over n to the n minus 1. So that's our next result. And similarly, looking at gamma 4, which is the lower path going to the right, we find that the absolute value of the integral over gamma 4 is also less than 3 over n to the n minus 1. So we have this 3 over n to the n minus 1, this one, and this one. So on each path, the absolute value of that integral is less than 3 over n to the n minus 1. All right, it's time to get to the residues. So let's calculate those. As I said before, the first order poles are at z equals plus minus 1, plus minus 2, dot, 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 plus minus capital N. And for this part, we're going to let k be a member of this set, plus minus 1, plus minus 2, dot, 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 plus minus n. And the residue of f comma k then equals the limit as z approaches k of z minus k over z to the n sine of pi z, simply z minus k times our f of z, since it's a first order pole. Well, we can pull out this z to the n, and this will equal the limit as z approaches k of 1 over z to the n times the limit as z approaches k of the rest of it, z minus k or sine of pi z. Well, this first limit is simply 1 over k to the n. And doing L'Hopital rule on this second one, these both go to 0, obviously. This will equal the limit as z approaches k of 1 over pi cosine of pi z as z approaches k. Multiplying that out, this equals minus 1 to the k over pi times k to the n. Cosine of pi k is simply minus 1 to the k in the denominator, which is the same as minus 1 to the k in the numerator. Okay, now we want to find the Laurent series of f of z about 0, because we want to find the residue at 0, but we don't want to take derivatives, nth derivative of f. That'll be much too complicated. So instead we're going to find the Laurent series. And this will be 1 over z to the n. That's the 1 over z to the n part. This part here in parentheses is the Laurent series of cosecant of pi z about z equals 0. You can find this in any calculus book. Capital B sub 2m is the 2mth Bernoulli number, as it's called. So this whole thing is the Laurent series of f of z. Well, what do we want to find there? We want to find the 1 over z term of this, and that'll be our residue. So where does 1 over z term come in? Well, we have a 1 over z to the n here. And we have a z to the 2m minus 1. Now, in other words, where is z to the 2m minus 1 over z to the n equal 1 over z? Well, that occurs at m equals n over 2. So you can see why we need n to be even here. So we simply plug in n over 2 for m here, and we get the residue of f at 0 equals 2 times the quantity 2 to the 2n over 2 minus 1 times the absolute value of b times 2 times n over 2 times pi to the 2 times n over 2 minus 1 over 2 times n over 2 quantity factorial, which simplifies to 2 times the quantity 2 to the n minus 1 absolute value of b sub n pi to the n minus 1 over n factorial, where n is even and n is greater than or equal to 2. Therefore, we now can say the integral over gamma, the total path of f of z dz, it'll equal 2 pi I times the sum of our residues, which is the residue of f at 0, plus the sum as k equals 1 to n of the residue of f comma k, the positive k's, plus the sum as k goes from minus n to minus 1 of the residue of f comma k again. These are all the negative k residues. Okay, writing that out, this equals 2 pi I times the quantity 2 times the quantity 2 to the n minus 1 times absolute bn times pi to the n minus 1 over n factorial, plus we can combine these two now, and since n is even, k to the n equals minus k to the n, and that's where this 2 comes from. We just double up everything, so this is part is the sum as k goes from 1 to n of 2 times minus 1 to the k over pi times k to the n. Remember our residues were minus 1 to the k over pi k to the n there. And we just combined these two sums into one sum by multiplying by 2. Now let's go back to the our absolute value of our integral over gamma. Remember, each one of those, the absolute value of each one of those was 3 over n to the n minus 1. So if we take the absolute value of the whole integral over capital gamma, this is going to be less than 4 times 3 over n to the n minus 1, which implies, of course, the limit as n goes to infinity, and n stays a natural number as it goes to infinity, of the integral over f dz over gamma equals 0. All right, we're almost there. So now let's go back up to here, our equation. We know now that this left side is 0 here. So let's bring this stuff over to the left side. First, we can divide by the 2 pi I, because this is 0 over here. So this implies 2 over pi times the sum as k goes from 1 to infinity of minus 1 to the k over k to the n, that's just going to be this part, will equal minus 2 times the quantity 2 to the n minus 1 absolute bn pi n to the n minus 1 over n factorial. Okay, bringing the 2 over pi over to this side. This implies the sum as k goes from 1 to infinity of minus 1 to the k minus 1, I'm bringing the minus sign back over to here, over k to the n equals quantity 2 to the n minus 1 absolute bn pi to the n over n factorial. I multiplied the top by pi and I canceled the 2 when I brought this over. Okay, you'll notice that this is just a zeta function, the alternating zeta function. But from this, we can calculate the zeta function of n. and that'll equal 2 to the n minus 1 pi to the n absolute bn over n factorial, or n is even and n greater than or equal to 2. Why can I say that? Because we know that zeta of n times the quantity 1 minus 2 to the 1 minus n equals this alternating zeta function. And I hope you enjoyed the video. If you did, please give it a like. Thank you.